Light.
Mm.
Yeah, the stuff that lets us see.
Mm.
Well, what if it's not just passive? What if it's actually like an active sculptor, constantly creating and transforming the very fabric of reality?
It is a truly mind-bending idea, isn't it? And our mission today in this deep dive is, well, it's to explore exactly that, these remarkable abilities of high-energy photons.
Fundamental particles of light.
Right, and how they really challenge our everyday understanding of, what's possible.
Absolutely. And we're digging into this using insights from a source called Photons, Matter Creation, and Nuclear Transmutation. It really shines a light, you could say, on how connected energy and matter are.
It really does. It's the kind of thing that makes you see the world a bit differently.
Yeah.
And what's fascinating is how it links straight back to Einstein's famous equation, E-mco.
Ah, the classic.
It's not just an equation on a blackboard, is it? It's telling us something profound, that the vacuum of space isn't really empty.
Right. Not just nothingness.
No, our source actually describes it as a seething cauldron of potential particles, which is quite an image.
A seething cauldron.
Yeah.
I love that. It challenges that whole idea of empty space, like it's just waiting to burst into existence.
Precisely. Blurring the lines between, well, existence and non-existence, fundamentally.
So what can you expect from us today? We're going to unpack two really mind-bending processes.
Okay.
First, how light can literally create matter and antimatter, seemingly out of nothing. And second, how those same photons can, well, reshape atomic nuclei, actually change elements. It sounds like alchemy.
It really does. Cosmic alchemy, you could call it. So let's start with that first one, light creating matter. It's a process known as pair production.
Pair production, okay.
A really high-energy photon, if the conditions are right, can just, well, spontaneously transform into a particle of matter and its antiparticle.
Hold on a second. A photon just becomes an electron and a positron. That feels, well, it feels like magic. Where does the matter come from?
It definitely feels like magic, but it's pure physics. I mean, think about it. For centuries, people dreamt of turning lead into gold, right?
Yeah, alchemy.
Here, light is doing something even more fundamental, creating matter from energy. The energy is the matter. That's what imparted tells us.
Wow.
And the most common way this happens is exactly what you said, creating an electron and its antimatter twin, a positron. But, and this is crucial, it can't do it alone.
Ah, okay. It needs...
What?
Like a catalyst?
Sort of. To satisfy the basic laws of physics, conserving momentum and energy, this creation has to happen near something else, in the presence of another body.
So it needs a dance partner. It can't just happen out in the void.
Exactly. That dance partner is usually the strong electric field around an atomic nucleus, or sometimes even another photon, though that's rarer.
And the photon's energy is key here.
Absolutely critical. To make that electron-positron pair, the photon has to have at least enough energy equal to their combined rest mass.
So there's like a minimum energy cost, a cosmic price tag for this creation. Does the source get into the specifics?
It does. For an electron-positron pair, that specific energy threshold is 1.022 mega-electron volts.
1.022 MeV.
Okay, and if the photon comes in with more energy than that minimum, well, the extra energy isn't lost. It gets converted into kinetic energy, meaning the new electron and positron fly off, basically. They get sent hurtling in opposite directions.
I'm trying to picture that nucleus involved. So it's kind of just sitting there acting as an anchor to soak up the recoil so momentum is conserved.
That's a really good way to think about it, yeah. An anchor. The nucleus is much heavier, right? So it can absorb that momentum kick without really gaining much speed itself. It keeps the energy books balanced.
Makes sense. And you mentioned photons interacting with other photons?
Yeah.
The source called that the Breit-Wheeler process? Sounds very sci-fi.
It does, doesn't it? It's a very direct way two photons collide, annihilate each other, and boom, you get a matter-antimatter pair. It was predicted theoretically for a long time, but it's actually been seen experimentally now at places like RHIC, the Relativistic Heavy Ion Collider.
So wait, scientists are actually making matter from pure light in labs. That's just wild.
They really are. They accelerate heavy ions, like gold ions, incredibly fast, close to the speed of light. These fast ions generate super intense electromagnetic fields around them, which are essentially like dense clouds of high-energy photons.
Virtual photons.
Effectively, yes. And when two of these ions collide, or even just pass very close, those photon clouds can interact. The photons inside collide.
And produce electron-positron pairs.
Exactly. Giving us a direct window into watching light turn into matter. It's pretty amazing stuff.
Okay. So light can create matter, My mind is already a bit blown.
Right.
But then there's the second thing, how these high-energy photons can mess with atomic nuclei directly, alter them.
Right.
This isn't just creating particles, this is reshaping existing atoms. Tell us about that.
Yeah.
Photodisintegration, was it?
Photodisintegration, yes. And if you think about the energy involved, we're talking high-energy photons, usually gamma rays. They can literally shatter the core of an atom.
Shatter it.
Well, when a gamma ray with enough energy hits a nucleus, the nucleus absorbs it. This puts the nucleus into an excited, unstable state.
Too much energy.
Exactly. And to get back to stability, it has to shed that energy. It does this by ejecting particles. It might kick out a proton or a neutron, or sometimes an alpha particle, which is basically a helium nucleus.
So it's not just an energetic nudge. It's like the photon makes the atom, well, throw up parts of itself.
Huh. That's one way to put it. And the key thing is, this changes the atom's identity. It's nuclear transmutation.
So changing the element.
Or the isotope, yes. For example, take beryllium-9. If it absorbs a high-energy photon, it can become unstable and spit out a neutron. What's left is beryllium-8, a different isotope.
That's a fundamental change.
Right.
Is there an energy threshold for this too, like pair production?
Absolutely. And it varies. It depends on how tightly bound the nucleus is, its binding energy. For instance, to break apart deuterium that's heavy hydrogen, 1 proton, 1 neutron, you need a photon with at least 2.22 MeV. That's the energy needed to break that proton-neutron bond.
And this isn't just happening in physics labs, right? The source mentioned it's important in stars, massive stars.
Hugely important, especially in things like supernovae. In the incredibly intense environment inside an exploding star, there's a massive flood of gamma rays.
Right.
And this intense gamma radiation can actually break down heavier elements that the star created during its lifetime.
So the elements are being unmade by light.
Exactly. It means the very elements that make up, well, us and planets and other stars, they might have been shattered and reforged by light itself, maybe multiple times. Light acts as this ultimate cosmic recycler.
That's profound. The universe constantly building and unbuilding itself with light. But how do we know this is happening? We can't exactly, stick a camera inside a supernova or watch a single photon interact.
That's a fair question. It comes down to decades of really solid experimental evidence. Way back, things like cloud chambers and bubble chambers gave the first visual proof. You could literally see the tracks of electron-positron pairs appearing.
Ah, the early particle physics days.
Exactly. And today, we have incredibly sophisticated particle accelerators and detectors. Places like CERN, SLAC, Jefferson Lab. These huge facilities are constantly studying these processes with amazing precision.
Refining the measurements, testing the theories.
Precisely. So our understanding is built on a really strong foundation of observation and experimentation.
So pulling it all together, what does this really tell us about light? It's clearly more than just illumination.
I think, in essence, seeing that photons can convert energy into matter and that they can reshape atomic nuclei, it just highlights how dynamic and interconnected everything is.
Yeah.
The universe isn't static. Light isn't just a passive observer, a messenger. It's a fundamental architect. It's actively participating in creating and changing the very substance of reality.
Wow. What an incredible journey we've taken today. I mean, thinking about photons just popping particles into existence and then also breaking apart and rebuilding atoms.
A lot to take in.
It really drives home that idea, doesn't it? Light is so much more than what we perceive with our eyes. It's this active, creative force woven right into the fabric of the cosmos, constantly shaping things.
It certainly is. And maybe that leaves us with a final thought to ponder.
Go on.
Think about every single photon streaming from the sun. We see it as light, as warmth. But each one carries within it this latent potential for, well, cosmic alchemy, constantly reshaping and creating the universe all around us in ways we're really only just starting to fully grasp.
So think about that next time you feel the sun in your face. And maybe wonder, what other fundamental particles out there might be silently, constantly reshaping our reality in ways we haven't even dreamed of yet? Thanks for diving deep with us today.